Hello everyone, Dr. White here with our final installment on sequences and series. We are now going to talk about Taylor series as opposed to Taylor and MacLaurin polynomials. You've probably been thinking, as we have seen again and again, how the nth degree Taylor polynomial so often gets to be a better and better approximation to the function as the degree n goes to infinity. You're probably wondering, like, well, okay, what if we didn't stop adding on higher and higher degree terms? What if we made a series out of the Taylor expansion instead of just, stopping at some n degree polynomial? Would we get the function itself exactly? And so that brings up the notion of Taylor series. The Taylor series for a function f of x centered at some number x is c, so they're changing their notation now from an a to a c, where you're centered, is t of x, and I kind of really wish they'd written a c in there somewhere because it depends on the center, and it's the same thing as the Taylor polynomial, except you never stop. So f of c plus f prime of c times x minus c plus the second derivative at c over 2 factorial, x minus c squared, and so on. In summation notation, same as Taylor polynomial, except that you don't stop at some top number. And so because you don't stop, we at some number little n, we now are just going to go ahead and let little n be the index variable in the summation, because that just feels more familiar to us from our original study of series. And so the general term that we're adding up is nth derivative at c over n factorial x minus c to the n. But the n could start at 0, which gives us the f of c. It could be 1, it could be 2, and it does not stop. So we get an infinite series. And if we choose to make the MacLaurin series, if that is, we choose to center at c as 0, then that's the special kind of Taylor series, and the general term would be nth derivative at 0 over n factorial, and then here we have an x minus 0 to the n, just an x to the n. So these are infinite series. And so I am not saying right now that the Taylor series or the MacLaurin series is guaranteed to be equal to the function. That does not always happen. But at least we can construct these series and we can ask the question about what they converge to. So let's do an example right after I get my coffee. Let's make the MacLaurin series for f of x equal e to the x. So we're centering around c as 0. And so the series is called t of x, and it's the sum. N goes from 0 to infinity, x to the n over n factorial. So if we write out the first few terms, it looks like that. And my question is, does that series converge to e to the x for all real numbers x? Well, it does. And let's see why it does. Well, I can certainly try to write that e to the x is equal to the sum of the first n terms of the series, capital N terms. So I'll call that t capital N of x. It's the nth degree Taylor polynomial, plus e to the x minus that nth degree Taylor polynomial. See, all I've done here is I've added on and taken away the nth degree Taylor polynomial. So I have not changed the thing I'm working with. It's still e to the x. But I've written in the form of an nth degree Taylor polynomial that you might try to approximate e to the x with, plus the error in that approximation. And my goal is to show that that error goes to 0 as n goes to infinity, no matter what x is. It goes to 0 as n goes to infinity. Okay? If I show that, then that means that this partial sum of the Taylor series, that n degree Taylor polynomial, does have to converge to e to the x. Okay, so that's my goal. Show that that goes to 0, no matter what x is. Goes to 0 as capital N goes to infinity, no matter what x is. That's my goal. Well, the error-bound theorem from the previous section is probably going to help us out here, because it says that the size of the error is less than or equal to an upper bound, we'll talk about that in a minute, times x minus 0. So your center is 0, and you're going out to little x minus 0 to the capital N plus 1 over capital N plus 1 factorial. So what's that upper bound? Remember, that upper bound is the upper bound on the absolute value of the n plus first derivative of your function on the range from 0 to the x that you're working with. Okay? Now this time, our function f of x is e to the x. And so its derivative is e to the x, and its second derivative is e to the x, all the way on down. The nth derivative of our function is e to the x. So as a function of u, the nth derivative of u is e to the u. And here I am making a graph of y equals e to the u. Okay, so we just have that familiar rising graph. It goes through 1 when u is 0, and then it's, rises quickly. And so here's the u-axis, and here's the y-axis, this little vertical thing. And I'm interested in the range on the u-axis from 0 to x. So I've graphed the end of that range. This point here is x comma e to the x. And I think, what's the biggest sized value that I see there? Well, the biggest that I see is e to the x. So I could use e to the x as my upper bound. Okay. So I'm guaranteed that the size of the error has to be less than or equal to e to the x times x to the capital N plus 1 over capital N plus 1 factorial. Now remember, x is arbitrary, but once you've picked it, it's not what's changing here. As I take my capital N to infinity, the x is just staying what it is. The capital N's getting bigger. What's the limit as capital N goes to infinity of this part right here? Well, we have seen what that is. We know that factorials grow faster than exponents. We have seen that limits like that is 0. So this limit, which is just a constant times that, would also be 0. And so since this sequence is bounded above by that sequence, it has to go to 0 too. The limit in the size of the error is 0. So those partial sums, those Taylor polynomials, really do have to converge to e to the x, and they've got to do it for all x. Big thing to remember here. Very important, very useful, very common in your future work with calculus. E to the x is really just a glorified polynomial. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus and so on forever. It's really just a polynomial, an infinite degree polynomial, a glorified polynomial. This happened for a lot of functions. And it happens for a lot of important functions, commonly used functions. I'm going to show here some functions whose MacLaurin series can be shown to converge to the function either for all x or for all x in a reasonably big range. So you're going to need to know these. Sine of x. If you just take those Taylor polynomials and take those MacLaurin polynomials and just keep going forever, you've got the MacLaurin series. So you could write that out like this. This captures the alternating sum. Here we've got the odd powers and the odd factorials on the bottom. That works for all x. You can use a similar argument to what we did for e to the x and show that the error goes to 0. Cosine of x. here's the MacLaurin series, and there should be a plus dot 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 right after it. Okay, so this is on page 3. Let me fix that. Plus dot 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 equals. Okay. Should be a plus dot 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 right there. And so that can be written out like this. And again, the 2n captures the even powers that are involved. Another good one to know is log of 1 plus, natural log of 1 plus x. In the book, they derive the MacLaurin series for this one, and it turns out to be this. So it's alternating. You don't have factorials on the bottom, you just have increasing integers. And the way to think of it in summation form is to start with little n equals 1. And then do your x to the n's over n, and this will capture the alternation just fine for you. Now that one does not converge to log of 1 plus x for all x. For one thing, log of 1 plus x is not defined for some x's. You know, like if x were -2, you'd be looking at log of 1 plus minus 2, that's log of -1, but log of negative numbers is not defined. So you can't expect convergence for all x. But it can be shown that the convergence works for all x that are bigger than -1 and less than or equal to 1. In particular, the 1's kind of interesting. If you put in a 1 here, you get 1 minus a half plus a third minus a fourth plus a fifth and so on. You get that alternating harmonic series. And back when we studied alternating series, we found, oh, that one converges, you know, by the alternating series test. But what does it converge to? Well, guess what? It's going to converge to log of 1 plus 1, log of 2. All the time was log of 2. Anyway, I want you to know the MacLaurin series for the big 4 functions, e to the x, sine of x, cosine of x, and log of 1 plus x. They're just so useful in applications. Another couple of good ones to remember, they go all the way back to geometric series, and we kind of covered them again when we talked about power series, is that the function 1 over 1 minus x can be expanded as a power series, and that convergence happens for absolute value x less than 1. 1 over 1 plus x being 1 over 1 minus negative x, again, using your geometric series facts, can be expressed as a power series, this little alternating looking power series, okay? And I should say, and the book points this out in Theorem 1 in the textbook, that however you can get a function to be represented as a power series, if you can get it represented as a power series for some range of x's around the center of that power series, then you know that that power series would also be the Taylor series for the function. So like here, the center of this power series is a 0, x minus 0 to the n. So this is actually the MacLaurin series for 1 over 1 minus x. And this is the MacLaurin series for 1 over 1 plus x. Really common in applications later on with calculus that you'll need to be able to express a function as an infinite series. So I'm just going to show you some shortcut ways to get some familiar looking functions expressed as infinite series. What about e to the 2x? You don't necessarily have to go and like find the general terms of the Taylor series, of the Taylor polynomials like we did in the previous section. You could just use the fact that you know the MacLaurin series for e to the x and just substitute into it. So e to the x is, you know, this infinite series here. That's just the MacLaurin series, x to the n over n factorial. And so you've got that in your head, okay? And so you can say, well, e to the 2x must be what I would get by putting a 2x where I saw an x in the infinite series for e to the x. And 2x to the n is 2 to the n x to the n. And if I wanted to write out some terms, I could do that. And because the MacLaurin series held good for all x it's going to hold good for all 2x's, which is the same as holding good for all x's. This equality here works for all x's. If you need sine of x squared, no problem. Just hit up sine of x, okay? And put in an x squared wherever you see an x in that summation. And so you'd come to this. And then if you wanted to write out some terms, let's give it a try. When n is 0, this is a 1. This would be x squared to the 1 over a 1 factorial, which is a 1. So we only end up with the x squared. When n is 1, then you are going to have a negative. Okay, it's right here. And you got an x squared to the 3. X to the 2 to the third is x to the 2 times 3, which is x to the 6. And on the bottom, you've got your 3 factorial. And it would go on like that as long as you wanted to. And remember, the real good use of this is that if you need to approximate sine of x squared for some number, you could just, take some of these terms and add them up and get an approximation, and the approximation would be better the more terms you take. What about something like x times the cosine of 3x? Well, I would leave the x alone for now and just plug 3x in where I saw an x in the summation for the MacLaurin series for cosine of x. And let me see, 3x to the 2n would be 3 to the 2n times x to the 2n. And 3 to the 2n is actually 3 squared to the n, so 9 to the n. And then you could write out terms if you wished. But also you could take the x and you could just multiply it in, distribute it in to the sum sign, and get an x to the 2n plus 1 inside the sum sign. So I won't, so anyway, there's a summation version of x times cosine of 3x. And if you want to practice writing out some terms, setting the n to be 0 and then 1 and then 2, that's good practice, and you should give that a try. If you've got x squared over 1 minus x to the 4th, I would say try to relate that to the 1 over 1 minus x. So this is something we actually already know how to do from our work on power series. We're just sort of reviewing. I'm thinking of it as x squared times 1 over 1 minus x to the 4th, but I've written x to the 4th as x squared squared. So I can relate to the 1 over 1 minus x. And so then I've got x squared times the power series for 1 over 1 minus x, but I plugged in x squared where I saw an x. And this is x to the 2n. And if I distribute in x squared, I'd get x to the 2n plus 2 as a power. And again, you can practice writing out some terms. It gets a little tougher if you're looking at, say, f of x is e to the x times cosine of x. And so there, you've got two functions that each have their own MacLaurin series. And so it's going to be hard to get like just the general expression for the MacLaurin series for the product of those two functions. But you can get Taylor polynomials as high as you want. Like say you want the third Taylor polynomial, okay? Let's say we want to get to the third degree. What I would do is I would take the e to the x MacLaurin series and write out the terms to it third degree. And I'm doing plus, 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 so I can capture the rest of e to the x. And I'll do cosine of x, and I'll do the same thing. I'll write up to the third degree. And so I get 1 minus x squared over 2 factorial. The next term would be a plus x to the 4th over 4 factorial, so I can stop right there. And then I'll just multiply, this, times this, okay? And so I would have 1 times all this, that's here. And then I would have a minus x squared over 2 factorial times all this, and that's here. And there, of course, would be higher degree terms past this. I just haven't, written any of them down, okay? And I'm going to gather like terms. I only see one constant. I only see one x. I got an x squared over 2 factorial, but it gets canceled by this. So there's actually no x squareds at all. Are there any x cubes? There's an x cubed over 3 factorial and a minus x cubed over 2 factorial. So I've got, if I factor out the x cubed, I've got that. And everything else is higher terms, x to the 4th and x to the 5th. And I said I didn't want to work with them, so I'm just going to write plus higher degree terms here. And if I work this out, that's a 6th minus a half, which turns out to be a minus a third. And so there's the first 3 terms of the MacLaurin series for e to the x times cosine of x. I could get more terms if I did more work. Here's an interesting application. Lots and lots of integrals that we can't find exactly. Here's one of them. The definite integral from 0 to 1 of e to the negative x squared. And the reason we can't find it exactly is we cannot find a closed form antiderivative for e to the minus x squared. We could use things like Simpson's rule to approximate it. But you can also use your infinite series knowledge. Take your integral and get a MacLaurin series for the integrand. And so I plug in a minus x squared where I used to see an x in the MacLaurin series for e to the x. And probably the easiest thing to do from this point is to write out the first few terms. So I did that. And then let's apply fundamental theorem calculus. Let's find antiderivatives and evaluate between 0 and 1. And so I've got this, got to do an antiderivative of this sum. So I do the sum of the antiderivatives. Antiderivative of 1 is x. Antiderivative of minus x squared is minus x cubed over 3. Antiderivative of that is going to be an x to the 5 over a 5 times the 2 factorial that's still in the bottom. For this, the antiderivative is a negative x to the 7 over 7 times the 3 factorial still at the bottom. Next up is x to the 9 over 9 factorial over 9 times 4 factorial. And, minus and plus forever. And I got to evaluate between 0 and 1. So I plug in 1, and I plug in 0. When I plug in 0, nothing comes out because I've just got little powers of 0 here. So all I've got is what I have when I plug in 1. And so I've got this alternating series. And I need to think what's a pattern for it? And so when I look at it, if I think of it as the sum, little n goes from 0 to infinity, minus 1 to the little n would capture the alternation. Minus 1 to the 0 is positive. Minus 1 to the 1 is negative. That captures the plus and then the minus. And I seem to have odd numbers, like a 3 and a 5 and so on. And so I've got a 2n plus 1 here. And then I've got my term factorialed. Okay, so I've got an n factorial here. That works to capture all these terms. Let me check the 0th term. If I plug in little n is 0, I get minus 1 to the 0, which is a 1, over a 1 times a 0 factorial. So 1 over 1 times 1. 0 factorial is 1. So yeah, I do get a 1. It really works for all the little n's. It captures this series exactly. So, now we could try to make an approximation. For example, what if we approximated this integral with maybe just the first 4 terms of this series? So that's out to here. And if I do the math on the denominators, it turns out to be these things I got to add up. What would the error be if I were to use that approximation? Well, this is an alternating series here. And we have a theorem that when an alternating series converges, the error in approximating by the first capital N terms is smaller in size than the first term that you did not include in your partial series, in your partial sum. And so the error is going to be smaller in size than that, the first term not included. And that works out to 1 over 216. So the error is fairly small. But suppose I wanted to really get a great approximation. Like, how far out in this alternating series would I need to go so that our approximation would be accurate to 3 decimal places? How would I do that? Well, let me make a note here. Accurate to n decimal places means that your error has to be less than 5 times 10 to the minus n plus 1. So in this case, we're asking for the error to be less than 5 times 10 to the minus 3 plus 1, 10 to the minus 4. Now, we know that the error in using the capital Nth partial sum is going to be less in size than the capital Nth plus 1 term, which I've written out here, putting a capital N plus 1 instead of a little n. And the absolute value of this is going to be a 1. And here we have a 2n plus 2 plus 1, which is 2n plus 3. And here we have an n plus 1 factorial. So we need to work it so that the error is less than that. We need to find an n so that this is less than the 5 times 10 to the negative 4, which, by the way, is 1 over 2,000. I need this to be less than 1 over 2,000. So multiplying both sides by their denominators, I need this to work out to be bigger than 2,000. And so what I could do is maybe pull out a calculator and try for a few small values of n, like n is 1, n is 2, n is 3, so on. And I've got a little table here for when n was 4, I got that this quantity was 1,320. Oops. Yeah. And let me fix the width. And when n was 5, it worked out to 9,360. I only needed it to be 2,000. This is not enough. This is more than enough. So I'll stick with the capital N as 5. That's going to do. I'm going to go out. I'm going to go out from 0 to capital N, 0 to 5. So I'm going to need 6 terms. And so my approximation is that this is supposed to be about equal to the 0th term, the first term, the term 2, the term 3, the term 4, the term 5, and I stop right there. And I could go to a calculator and find what that is. But I know it's going to be right to the first 3 decimal places. Okay, this is a good place to stop. We want to cover one more interesting feature of interesting application of what we know about MacLaurin series in the next screencast.